Welcome everyone. I've been working with Julia for around 4 years, doing also a bit of development of Julia itself. So I hope to show you why I use Julia and why you might consider also using Julia in your projects. I don't want to go into details about Julia. I will rather show you things and ask you to think how would you do such a thing on your current technology stack, and then I will show you how you do it in Julia. Because, of course, all the things you can do in Julia, you can do in any other language, because Julia, you can think it of like, you have R, you have Python, and you have Julia. So every language can do everything, more or less, but the question is how easy it is to do this. So I will talk a bit about handling of large data, about parallelization, about speed. This is probably the first thing you hear when you hear about Julia. And finally, some thoughts. Okay, can we go into production with Julia? So first, as I said, several warm-up questions. I think of yourself like me, so that you have this notebook I have there. So it's like standard notebook for writing emails. 8 gigabyte RAM, some i5 processor. So I have this laptop with 8 gigabytes RAMs, and I have 2 billion floats somewhere. Yes, and I want to work on it. Like calculating mean, this is what I will show, but in general, anything. Do a histogram, update this vector of 2 billion floats, and so on and so forth. You use probably Python, R, or whatever. Think of how you would do this. Of course, what is the problem? One float is 8 bytes, so actually this data set is much larger than my RAM. But I want to work it as if it would fit in RAM. So of course, there are packages that can do it in R or Python, no problem. The difference in Julia is just it's simply built into a language. So if I have a such a big vector, I simply can map it to a file, and it takes actually 2 seconds to load it. If I wanted to copy it, it would be 30 seconds. So it takes 2 seconds to load it, and then I simply say, OK, calculate me the mean. And of course, it takes some time because it has to read all this data and swap between memory and hard drive. But in general, I work with this as if it was simply a vector in RAM. And it's seamlessly built into the language. Of course, as I said, in R, you can do this because you have a package for memory mapped files. But this is an extension, and you have to learn a new syntax for the same thing you would do normally on normal arrays. So this is out of core data. But then there is a question, OK, something you probably do on Spark or whatever distributed system you would use. So for example, this is a real case. You have, I don't know, 4 years of data. Each day is 10 megabytes. This is high-frequency trading data from a stock exchange. So the plus is that the structure of every of those CSVs is the same. And I want to do standard things like filtering, mapping, joins, and so on and so forth. I won't show this here. And of course, I want to use all my cores to do the computations on this laptop. I don't want to, make some huge installation of whatever distributed infrastructure. I want to calculate it on this laptop. And again, I use the size because the size of data is too big to fit into RAM. So I won't show you the code, but JuliaDB simply distributes this. So DB is for distribute bytes. I tell Julia that I have a directory where I have those files, and it processes and distributes them across all my cores, and all those standard map reduce and so on things are provided by the language. So warm-up 2. Standard thing for any statistician doing bootstrapping. So you know that bootstrapping parallelizes very well. Yes, because you can actually, every iteration of bootstrapping can be done independently. The problem with bootstrapping starts if I want to distribute it among many cores that actually, I don't know, for example, in R, you would have to copy the same data onto every process. So again, if I have large data of large volume, very fast I will run out of RAM. And the second question is how to parallelize it, for example, in Python. I won't show you how you can do this. You could do this. But in Julia, again, this is pretty simple. So I first define an array, which I say that should be shared among all processes. Actually, when I start Julia, I tell Julia to automatically parallelize to all the cores I have. And then I have a comparison of two bootstraps. First bootstrap will just run on one core, and the second bootstrap here will automatically distribute among all the cores I have. So here, this is a standard bootstrapping procedure. So I won't discuss it in the detail. Here, the question is how does the one core code differ from the distributed core code? Simply, I spawn workers, and it automatically distributes among all cores. So then this PS vector will be actually vector of promises as in standard distributed calculation, and then I simply fetch those results and they execute in parallel. What is important that this array with the original data is shared among all processes. So there is no copying of the data. So why is it important? And I think it is most nicely summed up by the post of Julia joining the Petaflop Club. You might have heard it, that this is the only high-level scripting language which actually has a successful real implementation in which it reaches over 1 petaflop of performance. So if you would ask, okay, do I have such a big Python installation or R installations? There are none. Because at least as I know, and as you know, the Julia creators claim, because for example in Python, you know it very well, you have GIL, and there are some ways around it, but in general it is a hard issue, and in Julia it's simply inbuilt into the language that you can distribute your computations. So this is a second takeaway. Third takeaway, very simple. Actually, I have added this morning. I had some file, not very big, but it's an issue of scaling, some file of 15 megabytes of UTF-8 string data. Of course, it could be not 15 megabytes, but 15 gigabytes, it's no difference. So I want to read it into my memory. What do you think? How much memory it would eat up typical UTF-8 file in Python? It would eat up around 30 mega. Actually, this file, because this was actual file, it eats 30 megabytes of memory. In Julia, it eats 15 megabytes with some overhead, a bit. Why it's important? Because if you work with a lot of data, actually this will start hitting you. Because, of course, this is an example of UTF-8 files. If I had pure ASCII data, there would be no difference, or almost no difference. But for example, if I have UTF data, which probably most of us will have to handle someday, then you start to see the difference. And again, this is something just simply inbuilt into the language. Why? What is the reasons for the difference? If someone is interested, I can answer at the end of the presentation. So now, so those were the warm-ups. So things that you can actually do in other languages, but simply I believe that handling large data and distribution of computation is really simple in Julia because it's inbuilt into the language. But now the issue about speed and the discussion will be a very standard problem. This is a problem of pricing of Asian option. So the price of the Asian option is the formula is not so important. The issue is here that I have to calculate the average of some random stochastic process over some period and decide whether it's below or above the strike price of the option. So the standard approach to evaluate such an option is that you discretize the time into discrete periods. And here a standard approach would be to use geometric Brownian motion to simulate the move of the stock price. And then this is the recursive formula for the price of the stock. And then you simply calculate the value of this option, but by averaging a lot of samples of such a simulated process. So let's start my first implementation in Julia. I simply take those formulas and simply translate them to code. So this is actually one-to-one mapping of my formulation on a paper to formulation in the code. So for example, here I have this x hat, so x hat starts 0. I have those deltas, so I translate into those deltas, and simply this is a very simple looping code that you could write in some other language probably also. But what I want to stress here that is important, this is a nuance, but it's nice that actually I can use any Unicode as identifiers, which I am a researcher. This is important for me because this is something I would have in the paper, and I want a direct correspondence between the paper and the code. Why? Because if you look at a similar program in Python, doing exactly the same, so here I have, for example, this x hat, so I have to think that this is the same. But actually in Python, of course, this is the code in Julia, this is the code in Python. Of course, there are some differences, but in general, the idea of the code is the same. So here is one special thing. Probably we are at PyData, so everyone one day have used it. I use Numba to speed up the computations because so this just-in-time compilation directive tells me that Numba should compile this Python code to machine level to speed it up. And I will show you what is the difference between having and not having this decoration on this function in a second. The only caveat is, and people who have used Numba probably know two things about Numba. First is that not every Python code is a valid Numba code. And the second thing that not all expressions in Numba and in Python actually mean exactly the same. Which means that in this case, if I add this JIT, it does not change anything. But in general, if you want to switch from Python to Numba, you would have to run the test to make sure that your code actually produces exactly the same values, because it might not. Because Numba and Python are not 100% compliant, and it does not only mean that it won't compile, because, for example, comprehensions in Numba won't compile, but even if your code compiles, it might produce completely different results. But so I have this annotation. In this case, it gives the same result. So this is not a problem. I want to focus on speed more and to show you how this annotation changes the performance. Of course, I could, for example, write in Java. It's pretty much similar. If I wanted to switch to R, actually I have a problem because I implemented this looping approach, but this looping approach was problematic because it was so slow that actually I had to vectorize it. And after thinking a bit, you can devise a vectorizing approach to how to compute this recursive process. So this is the code. So instead of doing a loop, I allocate vectors and then do cumulative sum, which does almost the same. The only difference is that this code compared to this code, or this code allocates a lot of memory. Why? Because I have to allocate x and this here cumulative sum as some object in memory. And if I wanted to do a fine-grained simulation, actually this could be quite a lot of memory. But the question is, we can see that this code is shorter. Can I write it in Julia? Yes, you can write almost the same in Julia. So very similar syntax. I have only changed one thing. Here I calculate cumulative sum of x, and here I also do it, but I do it by updating vector x by the results of cumulative sum. So here R will create a new vector, and Julia updates the old vector. And I will show you how big difference this makes. This is something, actually, this is something not possible in R. R would allocate the new vector anyway, whatever I would want to do. So now the question, but besides of that, the code is very simple. So if I want to do a vectorized code, actually, I can also do it in Julia. So now, I would say the crucial thing, what are the results? So here I show how it scales with M, so how fine-grained the computation is. So this original Julia code, it's like runs instantly almost every time except for really large M, where it takes 1 second. This vectorized code so this code is slower, like 2 times slower. Why? Because it has to allocate memory. Also, the problem is that if M were really big, then I would have to ask myself, do I have enough memory? But we can see that for the sheer problem of allocating memory, this goes 2 times slower. But now let's compare this code in Julia to vectorized code in R. So it's like how it's 6 times slower compared to this, and like 10 times slower than Julia. So now Java is pretty fast, but actually not very good. The interesting thing is here, of course, everyone expected that this code in pure Python will be slow because it uses loops, and it is really terribly slow. In R, it would be even worse. Using Numba, I can speed it up. It's faster than anything except Julia, but it's still slower. And actually, as I said, it has 2 problems, that not all Python is supported by Numba, and you have actually to write tests anyway to check whether your Numba code produces exactly the same result. So this is a typical speed up you can expect when you write your own custom code. Because if you use simply libraries, so if you want to call TensorFlow, everyone talks about TensorFlow. So it does not really matter if you call it from R, Python, Julia, or whatever. Every language has bindings. But if you have to write your own code, so you are not only reusing someone else's work, but you are devising algorithms yourselves. And actually, this is what I do at the university, and that's why I use Julia. Actually, you will see a big difference. Just an example from business. This is a pretty well-known use case from Aviva. In Solvency II, this is a process of verifying if an insurance company has enough money to cover the potential claims that its customers might want. In such processes, usually you have to write custom code because every situation is a bit different, and you have to write custom code that calculates those risks. So Aviva reports that what they had earlier was, first of all, using Julia allowed them to reduce the amount of code they had to write to run those Solvency II calculations. And the second thing is that the code anyway was around 20 times faster. So on large deployments, it means going down from 100 computers to 5 computers. And of course, in the end, they said that because of all this, they have also lower license footprint, because for every server, it's not only server, but you have to buy software for it. So this is the case not from Poland, but actually, it was last week, I have a case from Poland. Ministry of Health in Poland, I don't know if you know, they run quite a big project of calculating forecasts and optimizing the data about what Polish citizens will, what health problems Polish citizens will have, and then what should be the optimal assignment of different medical facilities around Poland in order to have a matching of supply and demand. So this is the general project, and they do a lot of it in R. And actually, they came to me, and they had one of the problems they had is optimal allocation of accelerators in radiotherapy. So so what you have to do, you don't have possibility to have this accelerator in every city because they are very expensive. And actually you have to assume that people will have to travel to those accelerators in order to get a treatment. So then the question is, given the limited number of accelerators you can have, what are the optimal spots around the country where you should put them in order to minimize this travel time of the patients? So they had some code in R that did exactly the same, and it was like 500 lines of code. How Julia allowed me to reduce this code? If anyone was doing optimization in any language, of course not very simple optimization, but more complex problems in optimization, so you know that the real problem is that you have to transform, and this is what I hear on every talk, you have to transform your problem into matrices. So you have, objective function must be a vector. You have a matrix of coefficients for constraints and vector of right-hand side for the constraints. So actually, you have to do a lot of matrices and then push it to a solver. So, and this was the solution in R. And actually, ministry's problem was not that it was 500 lines of code, but no one could understand this code because they were, tweaking. So, for example, matrix B in row 20, column 25. If it's 1, that it means that something, and if it's 2, it means that it's something else. In Julia, for example, for optimization, you have a jump package, which is actually a domain-specific language built on top of Julia, which means that if I have such a problem, actually I don't have to care about those matrices. I can write a high-level code that will be automatically by Julia translated to this matrix language problem. So actually this code is 500 lines, but I don't have to write them because all those expressions here are macros that are rewriting this code, which is pretty simple to read. For example, variable y is a vector having L elements, and it has to be integer and non-negative. And this package allows me to rewrite all those expressions into matrices, but under the hood. So I don't have to do this myself. And actually, I would say that if you are doing optimization, so even today, Julia is a language of choice from any other language you might want to use, exactly because of how you can write optimization problems in Julia. But of course, not everything is so nice about Julia, because there are no free lunches. So of course, what are my experiences? So on the good side, let me start with this, is that if you are writing your own algorithms, then actually I think Julia is very good. One thing is the speed, but the other thing, and I didn't discuss it at all today, is how you can manage your code in Julia, because it allows you to structure your code much better than, for example, R scripts. The second good thing is that it has very simple bindings to more or less anything you would want to use. For example, if you want to interoperate with R, so you can call Julia from R exactly as if you would be using RCPP. If you ever used RCPP, so the package xrjulia is pretty similar, but it allows you to call Julia from R. So actually, if in the past you used RCPP because you had some hot code which you needed to run, you can replace it. If you know Julia, you can replace it by Julia. And I would say that writing code in Julia is simpler than in C++, if someone has experience with debugging C++ code. Of course, there is, and the interoperation is also simple in other ways. So there is a package in Julia, rcall.ji and JL, and it simply allows me to call any code, any function of R from Julia seamlessly. And the last thing, this is something I have shown here, that Julia has very powerful metaprogramming facilities, which means that actually it's not only that Julia itself is a nice language, but actually you can write your own DSL in the area you are working with, which will be built on top of Julia. So what are the cons? The first thing, and I think this is the biggest problem, that the language is still evolving, which means that it's not 1.0 version yet. So now it's version 0.6. We expect that, I would say, in half a year, there will be a version 0.7, which will be something like beta for 1.0. So the expectation is that after 0.7, there will be no language changes at all, and just the period between 0.7 and 1.0 will be a period for bug fixing the language. But this means that if you write a code today, unless you know what are the plans for the development of the language, because if I know more or less what is going to change. So I know where I can expect that some breaking changes might happen. But in general, if you upgrade Julia from one version to another, you may expect that not everything will work exactly the same, because the language is not in 1.0 version yet. And this is especially important in data science packages. So Julia has something similar to data frames, but the design of data frames is currently not stabilized, because people are working on making data frames fast with nulls. So this is something that is inbuilt in R. So this is something similar. We want to build in something similar into Julia. The issue is that if you want to be fast, so to have something like this also for data frames, this actually is a bit difficult. And this is a work in progress. But as I said, if you are writing your algorithms, I think those pros are overcoming those cons, because those changes are, it's not that the language totally changes. It's like single expressions change a bit. The last thing is something that is in some application a deal breaker, and this is something that I expect also that in 1 or 2 years or even 5 years will be a problem, that the difference between Julia and Python or R is that Julia is a compiled language and R and Python are interpreted languages. So if you use Numba, Julia is pretty much more or less similar to Numba. Yes, so if you use Numba in Python, actually the first time you run a function, it has to be compiled. And the same thing is with Julia. So actually you use it like as if it were a scripting language, but under the hood it has to do a compilation, which means that when you have a short program and you start it, the first time it has to be compiled, which can take some time. So for example, it's not an efficient way to use Julia to, I don't know, run 1,000 times a very small program per second, because startup and shutdown of the Julia environment will kill performance. It's much better to write programs that run and are listening to requests and responding to requests, for example, using ZMQ. So, and in some applications, this is a problem. And this problem probably will not be solved at no time, because, as I said, it's not an interpreted language, but a compiled language, and it has to do compilation anyway. It has to do compilation exactly because we want to reach this. Because the difference between this speed and this speed is that in Python, every line is interpreted, and in Julia, every line, a whole program is compiled to machine code, but then you have the overhead of this compilation, which you don't have in Python. So this summarizes what I think is interesting about Julia, why it's worth to have a look at it, but also what are the possible problems of using it. So thank you very much, and if you have any questions, you're welcome. Yes, so the answer is the following. The languages that have comparable speed to Julia in general are C, Fortran, of course, C, which means also C++, and just-in-time compiled Lua. So if you use just-in-time compiled Lua, also it is of the same speed as Julia. So in general, you can expect that a well-written code in C, Julia, or Fortran should be on the same speed magnitude. Maybe, of course, it is like 10% or 20% plus or minus. And actually, if you go to a Julia language website, I don't know, I don't have internet on, but on the first splash page, you will see a benchmark that answers exactly the same question. But in general, you can expect that Julia is the same speed more or less as C. And just to explain why, because how Julia works, it takes such a code, lowers it, of course, as every other language, then it passes it to LLVM, so like in Swift, and then LLVM compiles it to the machine code that is optimal for the machine you are running the program on. So actually, if you write properly Julia code, you can expect that there should be not a difference to a properly written C code, because of course you can also write C code badly. But in general, in the end, after compilation, Julia code is like C code. I mean, the executable. Because, of course, the language is different.
This compilation time is not a disadvantage. It's an advantage. It would be possible to save this result of the compilation. So the Julia each time interprets the program and it does not save the interpreted program or compiled program as a executable.
Okay, so this is a different, difficult topic, because in general, Julia is a compiled language, and it can store those compiled versions of the functions. The problem is, and actually, if you use Julia packages, this is exactly what happens. So Julia packages use pre-compilation. So actually, when you load a package, it's not compiled, but only an image of compiled package is loaded. The problem is that, for example, let's have a look at this code versus this code. In Java, I really compile the code only once. Why? Because I know exactly what types of data I will pass to a Java function. Yes, because I know this is double, and so on and so forth. I can do this in Julia, but in general, in Julia, you don't have to do this. That's why we use scripting languages. I write it like this. But this means that if I pass, for example, t as float, and in the second call, I would pass an integer to this function, it would have to be recompiled because Julia actually will take notice that it got a different type of data, which means that in general, this what you say happens, but the problem is that if you have a complex function signature, you won't compile it to any possible combination of arguments. And what Julia package developers do, they compile it for the most often encountered combinations of arguments. So doing something like this, allowing other types of data to be passed to the function, but if this new type of data is passed to the function, it has to be compiled just in time. So you can do a pre-compilation, but there is always a risk that you will use such a set of arguments to a function that it will have to be compiled just in time. Of course, this just-in-time compilation is not like 1 minute. It's relatively fast, but in real-time systems, even some time of compilation might be a breaking problem.
Parameters that are expected, and then you can recompile the start function each time. For example, if those parameters changes and
yes. So if I understand you correctly, this is what is done. But in general, if I put a type assertion to every expression here, then I would lose all the power of a scripting language. Because why we prefer Python to Java? One of the things is that we don't have to write those doubles everywhere. Yes, I simply write this, and Python will choose a proper function. And this is something that Julia can do. Of course, here, for example, I put this just to give an example. Here is a type assertion. So actually, I tell Julia that x will be a float. But I wouldn't have to do it. I can do this. I could even do this for every variable here, and then I could compile it, and it would be compiled. But for example, in Java implementation is that here I say it has to be double, and I would pass not a double to a function, and then it would simply not compile, and I would have to write another signature for a function that does not accept doubles and probably does some conversions. So, so in short, this is a complex issue. Because then you have in Julia type generics. So actually, you can have generic types that are typed by other types. And in such cases, it gets complex. But in places when you can do pre-compilation, the pre-compilation is done. It can be stored and then load from an image. OK, so thank you very much. And enjoy your lunch.